Really.
There we go, it's recording.
Cool.
All right. So, let's get started. So we're going to go over what goes into a board design and how it progresses through the different steps of everything, all the way from idea to final product and testing and integration. Starting with ideas and requirements, go through the block diagram, searching for components, more on the logistics of that, where to get it from and how they come, schematic design and what you have to do in there for testing purposes and stuff like that. Documentation and design calcs, that's super important for anyone else is going to be using your board, testing plans, sim tools, layout and routing, what you have to be aware of with that, the future steps of test plans. You have to make sure there's all the test points in there and stuff like that. Gerbers and how manufacturers will look at your PCB, how the PCB is actually manufactured, and through assembly, testing it and validation with hardware, and then firmware as well, and then a bunch of links. So basically goes through the block design, through schematic, PCB layout, and then finished product there. So we go over that. So we designed PCBs overall, more focusing this session on component sourcing, manufacturing, and assembly. We won't go too much into electrical design of the board, but only on where to get components from, how to and how it's manufactured, what you need in your design in order to validate and integrate properly with both hardware and firmware. And obviously, a bunch of designers, they get a personal interest in their board, and if someone else starts coming messing with it, changing components when they're testing, it can be a little stressful. So good design documentation, I found, is the best way to ensure that people take over your board when you leave the team or move on to something else, that they won't mess it up too badly. Starting with ideas and requirements. What does it interact with? What connectors do you need to interact with those devices? Is it microfit? Is it a custom connector that stays on our car charger? And what are the inputs and outputs, voltage and current levels that will affect your tray sizing and how you test it? If it's high voltage, then you need different testing equipment for that. And then you also have to be aware of the requirements on the connectors. The pin spacing has to be adequate for the voltage size you need. Like the high voltage 150 volts, some of our connectors don't have quite as big of a margin. The microfits are good for up to 200 volts. And then connectors will be able to handle higher voltage levels. Our car uses 150 volts max on its high voltage DC battery. But 200 volts is cutting it a little close. We'd like to be a little farther off of that. Having connectors that are at least rated for 300 volts or so when we're dealing with high voltage. And it's also, this is the easiest step to simplify the design act. Once you start the schematic, once you layout, then simplifying the design requires you to start over. Not always completely, but if you can simplify it at the start, that's always best. So you should be asking yourself questions like, do we really need this board? Do we really need it to do this thing, or can we do that in a different way? Do we have to hardware debounce the signal, or can we debounce it firmware? And the trade-offs of those, analyzing that to make the board simpler. Does it make sense to put this on another board? Fan control, for instance, do we need that on the DC-DC, or can we put it on power distribution? Are there off-the-shelf modules that do this, and do they fit for our application? I can save us a lot of time and energy. You just purchase it, plug it in, test it, and make sure it does what it's advertised to do. And then we don't even have to go through any schematic layout yourself or assembly. So that can be a huge time saver and cost saver as well. But this first step is always hard in optimizing for what it actually needs and what can be sourced to other boards. It takes a system level understanding of the car, and it just takes some time to get used to. So easy resources, we're all here to all the leads have a good understanding of the system of the car, the system level, and what all the boards do. So for designing or starting off, it's always a good idea to see what's out there and see what other systems are in the car that could either make use of this function or wrap this board into their board scope. So you start off with the block diagram. Break it down into sections. You need to get an idea of how your board will work. Creating a block diagram is also great to have documentation for other people that will be using your board in the future. And it helps you fix bugging as well when you're tracing the signal path through and the power path through to see where the issue happens. But you see just go through each block and test the inputs and outputs, and then you can determine which block is bad, and then further from there you can zero in on the component that is the issue. It's still easy to simplify here. In future steps, once I actually start the schematic, then it's a little harder. This is a little more down to the details than the idea and requirement section is. But the block diagram gives you the whole overview of the board without choosing any chips or digging through data sheets. So some tools to do that. OmniGraphal on Mac, Draw.io, which is a Google product now. Altium Shapes can do it right in the schematic editor and just put it as the front page of your schematic. That's very handy for anyone that's going to be looking at your board in the future and figuring out what it does. If anyone has any questions, feel free to check them out. For component search, once you have your block diagram down, you have to start figuring out what components you're going to use to achieve those functions. So our preferred suppliers are DigiKey and Mouser. Arrow is also a possible one. They do ship pretty well. They have a little bit less stock than Mouser and DigiKey usually do. Octopart is like a BOM management tool. DigiKey also has a BOM management tool as well. Octopart has a bunch of different suppliers listed in there, so it'll show you the price at DigiKey and Mouser and Arrow. So you can compare prices there. Usually the prices are very similar. It just helps to check if it's actually in stock and you can order it from there. For DigiKey and Mouser, they have like two-day door-to-door delivery. They have huge inventory. We like to call it BOM coverage. So bill of materials is all components that goes onto your board. And DigiKey will usually cover like 95% to 100% of the components on your board. With DigiKey and Mouser, you don't have to worry about fake parts. Some Chinese suppliers like to throw in some fake ICs, counterfeit ICs. They're not too popular with like the ST parts or S instruments parts, but for cheaper ones, it can be an issue of Chinese manufacturers copying ST design and not including some of the protection features. So we like to stick to DigiKey and Mouser. When you have team accounts with them, you can just send it to the university, and it goes on to our solar card account. For IC manufacturers, Texas Instruments, Infineon, ST, Analog Devices, Linear Technology, Microchip are all good ones. So that's we like to stick with those. They work, but obviously those are just the big ones that I can think of off the spot that I can throw in this. So there's definitely lots of others that are usable as well. I'd stray away from ones that have Chinese sounding names. I just don't want to get into issues with fake parts. A good question from Nita in the chat: has there ever been an incident where we've gotten a fake part on the team? I don't believe so, but I know there is some. If any of you are into lithium battery charging, there's a chip called the TP4056, and that has definitely been copied a couple times in China. with slightly different names, the 4056E, 4056C. They have the same basic functions, but some of their protecting functions and current limiting aren't quite up to spec with the original part. So not for us, but they do exist. Passive components, resistors, and capacitors, those are pretty hard to mess up. They're pretty simple. So LCSC is a component supplier in China that has amazing prices. So we bought a whole bunch from there, and basically bought all the components in our library that we can get from there. So we have all the resistors and capacitors that we ever want, pretty much. But yeah, same thing. DigiKey mouse are great for those as well. They're a little more expensive, so we won't buy thousands from there. But time you did a hammer $1, so it's not crazy. The other important thing to keep track of is automotive qualification. There's a specification called AEC Q100, and components that are tested to that specification have higher reliability in high temperature environments, high vibration environments, and EMC levels in automotives. So whenever we're searching for parts, we like to include that specification in our search filters inside DigiKey.
Also, something that would be really cool to add to this deck is we have like a pretty good Confluence documentation on how to like source parts from DigiKey and deal with all the filters, because there are thousands of parts for the function you're looking for. And it's actually a real skill to like be able to figure out what filters you need and what actual electrical requirements you do. So we have some Confluence pages, which would be great to look at. You could hopefully link.
Yeah, I'll put in the link as well. So when you're searching for parts, one of the specs is packaging. They give you one of the filters. There's a bunch of different options that can be confusing. But we'll go through them here. The first one is cut tape. It's on the left, in the bottom left. It's just a tape of components. You peel back a plastic layer to show all the components on there. Resistors and capacitors and some LCs usually come in that tape. It's very easy. It's super simple. Like small components fit in there really nicely and won't fall out. So that's the most common for resistors and capacitors. In your filters, you just hit cut tape if it's a resistor or capacitor, and then you're good to go. And then you won't need any of the tape and reel, which we'll discuss later. Tubes, those are more commonly used for ICs. They're just packaged inside an anti-static tube. They're good as well. The big thing to be careful of is if there are minimum quantities on DigiKey that are greater than 1. We don't want to be dealing with buying hundreds of ICs when we only need 2. So keep an eye out for that. For trays, it just sends a package. It's an IC and a tray pretty much. They're used more for large-scale manufacturing on pick-and-place machines. So typically they will have slightly higher order volumes, but they are available in minimum quantity of 1 usually as well. So for larger ICs, they might come in trays. Bulk components are just delivered in a plastic bag, sometimes with bubble wrap on them. Usually it comes like that from DigiKey Moser. So electrolytic capacitors or connectors will usually come in bulk. It's not really worth putting those inside another enclosure in your bag. Because when you're assembling them, connectors, it's usually human assembling them. So it's much easier for a human to sort through a bulk bag than it is for a robot to do it, so they don't worry about packaging it in a way that's consistent. Some that we don't like, tape and reel. It's cut tape, but it's on a reel. That one pictured is about 7 inches in diameter and has a couple thousand components on it. We don't want to pay for all of those. We won't ever use 1,000 resistors of a certain type. So, well, we might have like 10K resistors or 1K resistors, but we don't want to get it on a reel. Typically the reels are 10,000s, 20,000 components. We don't want to order any of those because that just adds extra inventory space and extra cost that we want to avoid. Digireel and mouse reel are tape and reel components. Come on a tape and reel. which is DigiKey's version of a tape and reel, where they will put your one-off components that usually come on a cut tape. They'll put them onto a reel for you so that you can automatically load it into pick and place machines, and they'll surcharge you for this to $10. The big catch here is that typically the part numbers are the same between cut tape and DigiReel. It's just a checkbox that you click, and it'll add like a postfix to the part number. So we don't want to be ordering, we don't want to have an $8 to $10 surcharge for any of our components. So when you're adding them to your component lists, make sure that that option is not checked. You don't want any surprises with that. So obviously we're on a limited budget. This link here is a guide from Texas Instruments on the types of packaging. Just has some better pictures as well. You can check it out if you want. For resistors and capacitors, there are a whole bunch of different sizes of components you can get. These are all the S&D versions, 0201, 0402, 0603, etc. That basically determines the length and the width. Those are imperial units. The imperial units are the most common. There are metric equivalents of it, but no one uses them, so we don't either. We stick with 0603 components because they're easy to hand solder, and especially for beginners, that's important. Soldering 0201 components by hand is possible, but it's a pain. 0402 components you can do if you're pretty good at it, if you've had some practice, but we stick with 0603 so that we can standardize on having one type of resistor in stocks that we don't need 5 different values, 5 different component sizes of each value of resistor. We just like to keep one on hand and use that in all our designs so we have less parts in our bins. For ICs, there's a bunch of different packages. QFN is the one with no leads sticking out the bottom in the middle of the page there. We don't like to use that one, or the VGA pins that have holes on the bottom. They have no exposed pins when you're testing it and you want to say measure the signal going into the input of that op-amp. If it's QFN, good luck measuring the signal unless you have the test point of your design. Also for inspection, when you want to check the solder joint to see if it's not a gold joint and see if it's not bridged, then you can't see underneath the chip without x-rays. So large manufacturers and PCB assemblers do have x-ray machines that they check all their joints with. We don't, so I like to use stuff that we can inspect visually. So the QFP, SYC, SOT, TSSOP, those are all packages that have pins exposed on the top layers. So we like, if you're choosing components, make sure to avoid QFN and VGA types. So in schematic design, there's a couple things you can do to make it easier to manufacture and test. One of the big things is to follow your block diagram so that when you are testing, you want to trace the signal through from input to filtering to signal processing and then output. That's easy to do. You can check all the components specifically that are involved in that signal chain easily within the schematics. It's like a linear design through it. One goes like left to right through your schematic and follows the signal path. That's very easy to trace when you're debugging. Sometimes it can't always be organized like that in the schematic, but the more order you can put to your schematic, the better. Adding notes is amazing because obviously there are a lot of stuff you do during schematic design that, yeah, I'll do this for this reason, or these components will heat up a bit, so make sure to place them not near any sensitive components. So adding notes is a great example of that. Making sure that you'll remember later when you're debugging that components will get hot, so you don't say touch them with your finger as you're probing the other signal. Net classes are these red exclamation marks here, and those are great for labeling nets if they're high voltage or high power. And you can auto-assign trace thickness to ensure that it has the proper spacing and proper thickness of the trace, so it won't heat up too much and won't ruin your board. Test points are amazing. Always include them. Be sure to include ground test points as well. So whenever you're measuring a voltage, you always need a reference. So that's what the ground test points are for. And labeling test points for what they're for also helps you when you're debugging. So you don't have to go through and check your schematic for which one was test point 3 again. You can just get right there. This is test point from ground on the low voltage side or whatever it is. And if they're not in there, then when you're debugging it and you find an issue that you have to probe a certain signal, you can always should have a test point. So you don't need one on every single net in your PCB, but it's always good to have ones in the few critical nets, such as after every block in the block diagram, you can test the inputs and outputs of those. Sheet and labels for subsystems, it's very easy to separate your schematic out in different sheets. If one sheet deals with high voltage, leave that all in one sheet so that any high voltage systems are easy to debug and you have it all in one place. Design counts and documentation. These are always good to keep. I like to say that you need to know what every component on your board does and why it was chosen. So power rating of resistors, values of capacitors, you need to know why those are there. Or else when you're debugging or when you're doing layout and say you don't know exactly why a component is there, you like to make some mistakes and put it somewhere where it's not optimally protecting the device or protecting the device that it's supposed to be protecting. So for decoupling capacitors, those should always be placed near the IC pins, but if you don't recognize that a capacitor is a decoupling capacitor, then you might accidentally place it somewhere else, and then the IC is left without a decoupling capacitor. So that's super important to remember every device on your component, every device on your circuit board does, and why it's there. Excuses like it was there before or it's in the datasheet recommended schematic, I don't consider them to be good answers. Other people might, but you still need to understand it no matter what. Even if you do end up going with the datasheet recommendation, you still need to understand what all the components are there and why the values are chosen to do what they are. If you don't understand it, you're just going to be delaying the research for someone else to do later when debugging is happening. Likely it'll be yourself that's debugging the board, so you might as well do it properly to start with. If you can't write it down in a design documentation guide, then I would say you probably need to do some more research and figure out like why it's there. There are a lot of times I've had no idea why I say value is there. And quick Google search or asking one of the leads, asking typing has helped with that. And it's just been quick, hey, why is E5 here in this position? And they got a quick answer. And it usually makes sense. So ask questions. Google is great too, but sometimes for our board specifically, it's good to ask the leads and people who design them. When you're debugging, it's super valuable to have this documentation so that because it takes some time from schematic design and layout, they have to send the board out to manufacturers and it takes a week or two for them to get back. And by then, hopefully, you'll have hopefully you'll remember most of it, but there's probably going to be some details that you forget. So having the documentation is super important so that you can remember that. Sim tools are an amazing way to know what measurements you're going to expect. So this is one of Ashmika's sims that she did. Ashmika, do you want to talk about this?
Yeah, sure. So SPICE sims are especially useful for like a variety of things. One thing is to measure the current and voltage expected at every node of your design, and therefore you can spec the components you need much easier. Like for example, for this SPICE sim, it was for a DC-DC discharge. It was really simple because once you make the sim tool on LT-SPICE, which is a free tool for us to use, you can then like probe on that design and look for the voltages and currents at different nodes and components. And so, for example, R2, like I was able to probe the current going through it and therefore make a good and solid decision as to why I'm choosing what resistor for what power rating. So it backs up your design, and you'll find if you have issues with your design, the sim tool is the way to like know. So I strongly recommend making simulations for all your like subsystem circuits.
Yeah, and for some of them that include ICs, it's a little trickier to do. Sometimes
Yes.
you find spice models for them, but typically it can be simplified. Say a load switch can be simplified into just a straight MOSFET.
Yeah, for sure. Also, LT Spice is made by Analog Devices. So like all their ICs will be found on there. In most cases, you can find your components on DigiKey and they have Spice simulations with them if they're like well-used ICs. But if they're not, you can hopefully find an equivalent on LT Spice in the Analog Devices supplier. So yeah, it's still possible.
Yeah. So through that simulation, you'll figure out possibly some points that you figure you might want to test out in the future. You definitely want to test your inputs and outputs. Let's say there's one node of your circuit that has a derivative current. You just want to make sure it isn't heating up too much. That's what your test bed will remind you to do. Always super important to make one because then we have a record of what was tested on the board and what wasn't. Likely it will not cover every single possible issue that could happen with the board. And that's why we keep documentation of it so that when you're testing it in the future and say you find a new bug, we can know what's already been tested and what works for sure. And we can basically start off on a much better, start off further ahead than revalidating the whole board. So the test points in your board needs to be designed into the board, obviously, because it needs to have pads. So the resistor and capacitor pads can be used as test points. But if you're trying to make an oscilloscope measurement on a component probe, on a component tab, then it's probably likely to slip off. Otherwise, you're going to have to hold it there while you're doing the measurement. And if you have 4 or 5 measurements you want to make, that's going to be tricky because you don't have 5 hands. So just adding a test point to the board, maybe a test point component that has a hook in it that will allow you to clip the oscilloscope probes into it. And that's much easier to test. The goal of the test plan is to prove that your board meets the requirements that you set out at the start of your design. So when you're doing all this testing, keep in mind that the certain requirements you have to meet are there. So that could be it has to operate from an input voltage of 9 to 15 volts, or it has to consume less than 100 milliamps in current. So testing those and testing for those operating conditions will give you a much better idea of how your board behaves as a whole system once it's assembled. But the harnesses are needed for the testing equipment. So if you're going to connect it to the oscilloscope or the power supply, multimeters or do a signal generator, you'll need to be able to connect to those pieces of equipment. So oscilloscopes, test points and ground probes, test points and ground pins, power supply, you need an input connector, which is on the board already. But to connect to the power supply, it'll be a nano pins to the output of the power supply. And then into your board will be usually a microphone connector. Also just need that harness to made up in order to test it under the different operating voltages, say for the power supply. For the layout, it is as much of an art as it is electronic design. I've seen some amazing PCBs that look really good as well as are functionally amazing. So it really does matter how components are placed. If you place them kind of willy-nilly all over the board, then it can be a little bit tricky to get a good layout. Or I'd say impossible to get a good layout if you don't get a ton of component placement. So ideally with that, you want to start with just show the rat's nest and all the nets going between the components, and try and make that as neat as possible. That's how I do it to start off. That's a good way to approach it. Obviously, there are different methods that work for everyone, but trying to make the net list as neat as possible, and then moving on to routing. The routing is super easy if the net list is already straight lines from component to component and not crossing too much. So one thing to keep in mind is that connectors, when you're removing them and putting them in, you need to have access to get your finger around and to press the tab. You can actually, all connectors have a positive locking element we need to push down. So we'll put two connectors right beside each other with that tab facing each other, and that's probably common sense. It's good to mention again. Labeling test points, again, make it easier for yourself on validation. The person that's going to make the harness for your board, say for the BMS devices, Liam's designing all the boards. Liam and James are doing a great job on that. But they're likely not going to be the ones that are making the harness connect to them. So if the person that's making the harness has a quick indicator of this pin which connects to cell 5 needs to go into this spot in the connector, that's much easier if it's pressed on the silk screen than if it's buried inside the schematic. That's just one thing to keep in mind for silk screening. Make it easy for other people to read your board as well. For thermal management, some of the components will get hot. Current sensor resistors or MOSFETs or LDOs can dump a significant amount of heat. So you have to keep that in mind. There are some simple calculations you can do for that. Dave Jones on the EV blog has a great video going over thermal design. That's linked at the end. You can look for that. Copper planes are basically heat sinks. So your ground plane and your power plane is a heat sink. And vias are used to move heat through multiple layers. So if you have a component on the top that gets hot, you can throw some vias on there and connect it to your ground net, as long as it is the ground component as well. That will help move heat through the layers. Also have to be aware of isolation, ESD protection, differential pairs routing, to ensure that, for instance, CAN is always has the same impedance for each positive and negative trace. And the biggest thing is to figure out how the board's going to fit in the car. That's going to dictate a lot of your connector placement. For instance, which connectors are on each side of the board, input-output connectors, power connectors, and then mapping holes. We don't want the board to bend and it's obviously in a high operation environment, so having more mounting holes is better. And if you're removing components, removing connectors from the board, that could bend the board a little bit. Bending can cause some cracking and shorts inside certain capacitors. So obviously we want enough mounting holes on the board to limit the bending. For most boards, just 4 in the corners is good, but for larger boards like solar, a few more mounting points is always good. So that's the minute here, so we'll stop this and then start a new Zoom call.
Yeah, cool.